Hello everyone, welcome to this lecture. In this lecture, we will see how we can calculate the electric field of a solid sphere. Now, we will be using the Gauss's law to find the electric field, and if you remember, the Gauss's law is, in general, the electric flux phi sub E equals the closed integral, and it's also a surface integral, so surface E dot dA equals enclosed charge divided by epsilon naught. Here dA is the area element, and E is the electric field in that surface, and Q enclosed is the charge enclosed by the Gaussian surface. Charge enclosed by the Gaussian surface. This is very important because you can't just take any charge and find the quantity that you are looking for. You have to take the appropriate charge. Okay, so say here we have a sphere. It's a solid sphere. Notice the green color, and the radius of this sphere is r. Okay, now a sphere actually have like two sides, inside and outside, so we'll call it region 1 and region 2. We will calculate electric field in region 1 and region 2. Let's start with region 1, that is inside the sphere. This is region 1. Now in region 1 I have a small blue sphere. Radius of the blue sphere is small r, and this small r is basically radius of the Gaussian sphere. Radius of the Gaussian sphere. This is very important because radius big R is the radius of actual sphere, solid sphere that we are considering, and small r is the radius of the Gaussian sphere that is inside this like big original solid sphere. This Gaussian sphere actually is a virtual thing to calculate electric field at the surface of this Gaussian sphere, that is distance small r from the origin or from the center of this sphere. So our formula is that E dot dA surface integral equals Q enclosed over epsilon naught. First, what is Q enclosed here? Remember, this is a solid sphere and we are considering uniform charge density. Uniform charge density rho. So what is the total charge? Total charge enclosed by this Gaussian sphere. To find that, we need to find the volume of the Gaussian sphere. Remember that this uniform charge density is a volume charge density because the dimension of rho is coulomb per meter cube, or you can say C L minus 3, L to the power minus 3. Okay, so we need to find the volume of this small r radius sphere, the Gaussian sphere, and that volume is V equals 4 by 3 pi r cubed. So the charge enclosed by this Gaussian sphere is QENC equals rho times V. Okay, rho is uniform throughout the sphere. If you know the total charge, you can calculate rho by Q total charge in this sphere divided by the volume. 4 by 3 pi big R cube, because total charge in the sphere of radius big R divided by the volume of the sphere of radius big R. Don't mix up these two spheres, otherwise you'll not be able to solve this problem properly. Now the left part of this equation, we need to evaluate the dot product first. Now notice that electric field always points outward if it's a positive charge. So let's consider that our Gaussian sphere encloses only positive charge. The net charge is positive, and in that case the electric field will point in this direction, radially outward everywhere. So whatever the electric field is at that distance or at that point from this center, its direction is going to be along r hat, radially outward. So the direction of this electric field, I can write it like E hat is basically r hat, radially outward. Okay, now the direction of dA, or the area element. Well, what is the area element? The thing is, you take a small patch in this surface. This is a 3D diagram, and what is the direction of the small patch? Well, it's a sphere, and the surface actually points outward from the center, and that is n hat here. In general it's n hat, but here it is n hat equals r hat. The thing is, electric field and the surface area element dA points along the same direction, and this results in E dot dA equals E r hat dot r hat dA, like this, and you have E dA, and there is no more like dot product here. So now this equation is like easier to integrate. Okay, let me rewrite it using newly found information. E dA equals Q enclosed divided by epsilon naught. Remember, Q enclosed is given by this equation right here. Now what is the electric field in a certain like region in this blue sphere? If you notice here, then the electric field will be like dependent on this distance from the center, that is r, and electric field here will be the same, because it's the same distance. Whatever the electric field is the same distance away from a specific point, the origin of this sphere. Or what I mean by that is that electric field will be uniform at a distance small r from the center, and if electric field is uniform, we can take it outside the integral and have it like this, Q enclosed divided by epsilon. Now what is this double integral dA? Well, integration is basically summation, and dA is the area of any small patch on this Gaussian surface, and if you sum up all the patches, all small patches, you get the total area of the Gaussian surface, and the total area is area of a sphere, which is 4 pi, and the radius of the Gaussian sphere r squared. So that's your integration area. So I can denote it by like big A. So here I have E A equals Q enclosed divided by epsilon. This equation is basically very important, because when you have spherical symmetry in your system, in the problem that you're trying to solve, this will help you to find the solution a lot quicker way, because you don't need to consider all that in every case if you have spherical symmetry. And other thing that I mentioned here. So electric field, well, the magnitude here 4 pi small r squared equals, what is Q enclosed? Is rho times 4 by 3 pi small r cubed. Remember, it's a small r divided by epsilon naught. What do you have? E equals 4 by 3 rho times 4 by 3 pi r cubed divided by 4 pi r squared, and you are left with 4 cancels out, pi cancels out, you are left with rho r over 3. Yeah, that's it. That's the magnitude of electric field at a distance r from the center of at this point of the Gaussian surface. Okay, so what is the direction? Well, we know the direction because we have used the direction here, which is r hat, radially outward. Okay, so put the r hat here. So therefore the vector E is rho r over 3 r hat, and this is the expression, the vector expression of electric field at a distance small r from the center. But remember, this r is basically greater than 0 but less than big R. This is very important condition, and you will see why in a few minutes. Now comes region 2, which is like outside the sphere. In the same way, this is region 2. The green sphere is our original sphere, and purple sphere with radius small r is our Gaussian sphere in this part of the problem. Okay, so I'm gonna go a little faster here. So we had EA equals Q enclosed over epsilon naught. Since we have a spherical symmetry here, we can use it. Here, Q enclosed is the charge enclosed by the Gaussian surface. Now, what is the charge enclosed? Well, densities rho is uniform, and you can say that the volume is 4 by 3 pi small r cube. But wait a minute, small r cube basically is a larger sphere, but there is no charges here or here or here. Charges are only inside this solid sphere. Therefore, we can't use small r here, unlike the previous case. Here is big R, only the sphere, the green sphere basically. So that's the Q enclosed. Now, what is the surface area? Here you can't use 4 pi big R squared because this area is the surface area of this purple sphere, the Gaussian sphere. Therefore, it must be 4 pi small r squared. And if you plug those in, you have E times 4 pi r squared equals rho 4 by 3 pi r cube divided by epsilon. And now you have, well, what is this rho times 4 by 3 pi r cube? This is the total charge, Q total. So you have Q total divided by 4 pi r squared epsilon naught. And if you remember, this is exactly the formula that we always use, that is Q divided by 4 pi epsilon naught 1 over r squared. And of course we use K Q 1 over r squared. And if you use vector notation, then it's nothing but K Q r hat over r squared. R hat points radially outward. Keep that in mind. And K here is well defined, 1 by 4 pi epsilon naught. Let's summarize what we have learned. Inside the sphere, inside or region 1, we have E of R as 1/3 rho R hat, and outside region 2, well, inside means R is greater than 0 and less than big R, and outside means R is greater than big R, which is E of R as K Q R hat over R square. Now if we want to plot it, then notice that these formula are not exactly the same. So this is our Gaussian surface radius. If we plot radius along this axis and magnitude of electric field along this y-axis. Okay, so inside the sphere, if small r is 0, the electric field will be 0, because 0 times something is 0. So inside the sphere, electric field increases basically linearly with increase of small r, and outside the sphere it actually follows inverse squared law like this, which is 1 over r squared, and this is just r. So that's how electric field behaves inside and outside the sphere. The maximum magnitude of electric field can be at the surface of the solid sphere, radius big R.